Hi and welcome back to my channel. Today I'm going to be doing a COMSOL tutorial on the buoyancy flow of free fluids, and this is from COMSOL's website, and I'll be using COMSOL version 6.0. This example follows the benchmark buoyancy flow posed by Davis for free fluids. So the fluid is bounded on all sides so it can flow freely within this domain, but it can't exit it. So some areas you might use this type of modeling, moving fluids in pipes along shorelines within lakes, somewhere where, in a region where buoyancy flow results from density that varies with temperature change. Delta temperature is going to drive the convective flow patterns. Iterative process is tuned for fast and efficient solution using non-dimensional parameters and a Bouyancy term for the buoyant drive with the laminar flow and the heat transfer and fluids interfaces. As an alternative, the same problem can be solved using the non-isothermal flow interface available from the CFD module or the heat transfer module. Here's figure 1. We've got x-axis, y-axis, and boundary conditions for the heat balance. So our right boundary will have T0 temperature, starting temperature of 1. The left boundary will have a starting temperature of 0. The upper left corner has P equals 0. As we already stated, the fluid fills the square cavity with impermeable walls, so the fluid flows freely but doesn't exit. And the right and left edges of the cavity are respectively the high and low temperature sources. The upper and lower boundaries are insulated, and the temperature differential produces the density variation that drives the buoyant flow. Laminar flow and heat transfer interfaces in this example are bidirectionally coupled. Alright, so the Bouyancy term defines a force dependent on the temperature and fluid velocity transports heat. It's possible to formulate the incompressible Navier-Stokes equation with the Bouyancy buoyancy term on the right-hand side to account for the lifting force due to thermal expansion. Okay, so here's the classic Navier-Stokes with our left-hand side and right-hand side, but we have an added term, the general expression for conservation of momentum of an incompressible Newtonian fluid, the Navier-Stokes equation here. The Bouyancy approximation states that the density variation is only important in the buoyancy term. If F equals rho g is the gravitational body force, then this will just become a direct substitution in the Navier-Stokes equation along with the density variations, linear dependence on temperature expressed by this equation. So these both get plugged in to the general expression for the Navier-Stokes. So rho appears here and here. It's being replaced by this expression, and then F gets direct substitution for rho g. So we end up with this equation for incompressible, or a conservation of momentum of an incompressible Newtonian fluid with the buoyancy term. To account for variations in the density of the fluid this here. And these expressions, the dependent variables for flow are u, the vector of fluid velocity, and pressure, p. So del u, the velocity vector, equals 0 because there is no net change in the x, y, or z direction, or x or y, since we're modeling in 2 dimensions, because the fluid can't leave, so it must be 0. Alright, and then we have T representing temperature. T0 is a reference temperature, G is gravity, acceleration, rho naught gives the reference density, mu is dynamic viscosity, alpha sub P is the coefficient of volumetric thermal expansion, and the heat balance comes from the conduction-convection equation, where rho naught is Cp times the velocity vector, del temperature minus del of quantity K, the thermal conductivity of del temperature equals 0. So as you can see, the driving force for both of these equations is the the temperature difference. Okay, for the Navier-Stokes equations, impermeable no-slip boundary conditions apply. The no-slip condition results in zero velocity of the wall, with pressure within the domain remaining undefined. Because the lack of information about P makes it difficult to achieve convergence, you arbitrarily fix the pressure at a point. Oh, okay. So that explains why we set P equals 0 here. This is just to give us some reference, some datum inside the domain, because you have to have that to model it. Okay, so the boundary conditions for the heat transfer interface are the fixed high and low temperatures on the vertical walls with insulation conditions elsewhere, which we already talked about. The model addresses a wide range of cavity sizes, fluid properties, and temperature drops using material properties set up with the non-dimensional Rayleigh and Prandtl numbers. The Rayleigh number is given by this expression. It's the ratio of buoyant to viscous forces. Setting the body force in the y direction for the momentum equation to Fy equals the Rayleigh number over the Prandtl number times T minus T critical, and the fluid properties to Cp equals the Prandtl number, and rho equals the kinematic viscosity mu equals K equals 1, produces a set of equations with non-dimensional variables P, U, and T. As the Rayleigh number increases, viscous forces decrease in importance. And the Prandtl number is given by this expression, the ratio of kinematic viscosity to thermal diffusivity. All right, so we can see by just doing a limit analysis for Rayleigh numbers, if the denominator represents viscous forces, then as the denominator goes to 0 or decreases, the Rayleigh number increases, goes to infinity. So that's the point they're making here. As Rayleigh increases, viscous forces decrease in importance. You can examine a wide range of scenarios, sequencing through different values of Ra using an auxiliary sweep. To that end, the element size near the prescribed temperature boundaries corresponds to the thickness of the boundary layer when Ra equals 10 to the 6th. The temperature boundaries are going to be the most important, the most critical to our mesh solving. The results in the figure indicate how the vigor and complexity of the convection increases at higher values of Ra as expected. So this is what we're going to produce. Dimensionless solution for buoyancy flow and a fluid-filled cavity at increasing Rayleigh number. Okay, so we're going to do a 2D model. And in the select physics tree, select fluid flow, single phase flow, laminar flow. Click add, and in the select physics tree, select heat transfer and fluids. And add, and then we're gonna click study and do a stationary study. Done. So we've got two coupled physics. We're using laminar flow and heat transfer. All right, for global definitions, in the model builder window under global definitions, click parameters 1. And in the settings section, we're going to enter these parameters. So TC, the critical temperature, is our low temperature. Description, low temp. T high is 1. So obviously these are modeled as normalized Prandtl number. P0 is 0. That's our reference pressure for the upper left-hand corner. Reference pressure. And RA is the Rayleigh number of 0. Rayleigh. Was I saying that wrong? Sorry guys, I was pronouncing it wrong. It's Rayleigh number, not Raleigh. So Rayleigh number. Alright, and now we're gonna make the geometry. So in the geometry toolbar, select square and build objects. So we're not changing anything from the default values. And next we're going to laminar flow SPF to define fluid properties, initial values, and volume force. So under SPF, under component 1, laminar flow SPF, click fluid properties 1. In the settings window for fluid properties, locate the fluid properties section, and for row we're going to change from material to user defined and type 1, and for mu we're going to again change from material to user defined and type 1. Row is in units of kilogram per meter cubed. Mu dynamic viscosity is in units of Pascal seconds. So now we're going to set initial values for laminar flow. So we'll click on initial values, and down for P, in the P text field, we're going to put P naught, which we already entered as a parameter in global definitions. And for volume force, in the physics toolbar, click domains. So I'm going to go up here to physics, domains, and click volume force to add this to the list under laminar flow in the model builder window. And now we're going to specify the F vector, the force vector, as a x component of 0, so that doesn't change. And then the y component's given by the Rayleigh number over the Prandtl number times the temperature delta. High temperature minus low temperature. And now we're going to add a pressure point constraint. So in the physics toolbar, click points and add pressure point constraint. Select 0.2 only. So that's the upper left hand corner. And for P, we're going to put P naught, P0. Now we're going to click volume force 1. And in the settings window for volume force, locate the domain selection, and we're going to choose all domains. Why didn't we just do that in the first place? I'm not sure why we had to choose the pressure point constraint before choosing the domains for volume force, but that was the order it was presented, so that's the order I did it. Alright, next we're going to heat transfer and fluids physics. So now we're going to set the fluid initial values and temperature conditions for that physics. So in the model builder window under component 1, heat transfer and fluids, click fluid 1, and in the settings locate the model input section. So from the PA list, choose user defined. And we're going to put P naught once again for the absolute pressure, fluid 1, and locate the heat convection section. From the U list, choose velocity field SPF. So now to couple it with the other physics, the laminar flow, single phase flow, we're saying instead of user defined, where we would tell it what the x and y components of the fluid's velocity is, we're saying just reference the velocity field calculated by this physics, because we've got two coupled physics here. Locate the heat conduction fluid section, and from the K list, choose user defined. So we're changing the thermal conductivity from material to user defined and inputting 1 watt per meter per Kelvin. And now we're going to thermodynamics fluid at the bottom here. And for fluid type, we're going to change it from material to gas liquid. From the row density list, we're changing to user defined and inputting 1 for the density in kilograms per meter cube. And then for gamma, all the way at the bottom, the ratio of specific heats. From the CP list, choose user defined and in the associated text field type parental PR. It's like CP is supposed to be 1 and gamma, or sorry, CP is supposed to be defined as the parental number and gamma is 1. Gamma just defaults to 1. So we've got to put 1 in there, which is the default value, but it said it can't be empty. So, alright, anyway. Moving on. So we're going to set the initial values now for the heat transfer. So we're going to click on initial values under HT, the model builder window, and then put TC as the temperature. This is the low temperature. And for temperature 1, so we've got to add a condition now. In the physics toolbar, click boundaries and choose temperature. Select boundary 1 only, which is the left-hand boundary. And in the settings window for temperature, locate the temperature section and put TC. So we've got the low temperature over here, high temperature over here. So for temperature 2, we're going to do the same thing, boundaries, temperature, and then click the right-hand side. And then we're going to put TH for the high temperature we set in global definitions earlier. And now we're ready to define the mesh. So in the model builder window under component 1, click mesh 1. In the settings window for mesh, locate physics controlled mesh, and from the element size, choose extra fine. So we're changing this from normal to extra fine under physics controlled mesh. And now we're going to modify the edges. In the mesh toolbar, click edge. Select boundaries 1 and 4 only, so the left and right hand boundaries. And size 1, we're going to right click edge 1 and choose size. So now you'll see size 1 appears under edge 1. So this is different than the size that's global for mesh 1. Now we have a size 1 specifically for these domains we've chosen, or boundaries we've chosen. Okay, so size 1, locate the element size section, and from the predefined list, choose extremely fine. Alright, and now we're going to add a free triangular mesh. So from the mesh toolbar, click free triangular, and in the settings, build all. Alright, so what have we got here? The size that we defined here is saying, so we've got a size for the overall domain inside this unit square. And then what we're saying is we want a finer element size at the boundaries because of this background information we discussed earlier. Because where there's a higher temperature, you'll have a higher Rayleigh number. And that's really where the definition of the mesh becomes more important to the iterative solver, because it depends on the closest node or the node prior to it. So you want more resolution in solving where you have higher Rayleigh numbers. Continuing to study 1. In the model builder window under study 1, click step 1 stationary. And we're going to add a auxiliary sweep. So in the settings window for stationary, click to expand the study extensions. So this bottom drop down menu, we'll expand that and select the checkbox for auxiliary sweep. And then we're going to add by clicking the blue plus icon at the bottom and changing the parameter for sweep from TC to Rayleigh number. And we're going to input the following settings: 1E1, 1E2, 1E3, 1E4, 1E5, and 1E6. So those are just space delimited, and that's it. So now we're going to hit compute. Alright, so it's all finished. Got our results, manipulation next, and then we'll be done. So, velocity SPF. The first default plot group shows the velocity magnitude. Notice the high velocities near the lateral walls due to buoyancy effects. So just looking at the default plot, it's on the velocity surface plot already. So this is in meters per second, with the red representing high velocity, about 300 meters per second, and blue is 0. So we have no slip on all 4 walls. And then higher velocity where we have the high and low temperatures, which makes sense since that is driving the convective flow of the fluid. And pressure, the second default plot group shows the pressure distribution. So I'm just going to go down in the model builder window and click on pressure contour, but you can see that at the upper left hand corner, where the only point where we defined a pressure, P naught, was 0, you can see 0 would be this kind of reddish orangish color, and that is the line here. And the third default plot group shows the temperature. So I'm going to click on the third plot here, which is a surface plot in Kelvin. The temperature field as a surface plot. Add arrow and contour plots of the velocity field. Okay, arrow surface. In the model builder window, expand results temperature HT node. Right click temperature and choose arrow surface. So I just right clicked here, and then I'm going to select arrow surface so I can add arrows to my plot. I'm going to coloring and style, right here, select the scale factor checkbox. And in the associated text field, instead of 1, we're going to type 2E negative 4. So that's the scale factor for the tail. Right, and from the color list, choose black. So we have black arrows that show up nicely on this yellow and purple scheme. And then click plot, and now you can see. So the temperature surface plot itself is a result of 2 coupled physics. Because remember up here, when we input the heat convection velocity field, we said use the velocity field from SPF as your input. So the resulting surface plot is only going to show the temperature, but it won't have any information about the velocity field, even though the velocity field was used to derive it. So when you add arrow surface, the expression here, x component is u meters per second, y component is v meters per second. So we're adding information and adding utility to a single plot by visually representing something that was kind of there but not readily visible. Okay, so next we're going to the contour plot. In Model Builder window, right-click temperature and choose contour. So we're going to add a contour to this temperature surface plot. And we're going to replace expression in the upper right-hand corner of the expression section here, this red and green arrow icon. And from the menu, choose Component 1, Laminar Flow, Velocity and Pressure, and velocity field, meters per second. Here's that. Velocity field, X component. So we'll just double click on that and it'll populate the expression here. Locate the coloring and style section. From the coloring list, choose uniform. So in your coloring style, coloring, instead of color table, we're going to do uniform, and for the color, choose gray. Clear the color legend checkbox, and then plot. Oh no, we're not plotting yet. So for buoyancy, right-click temperature HT, and rename. So now we're going to call this, instead of temperature HT, it's going to be labeled buoyancy. And now in the settings window for 2D plot group, locate the data section. From parameter value array list, choose 1000. So we're changing from 1E6 to 1000. And in the buoyancy toolbar, click plot. So you can see when I define the contour surface, I never actually hit plot, but then by doing the next action, it just automatically plotted those gray contour lines. And now we're changing the source data from Rayleigh values of 1E6 to Rayleigh equals 1000. Okay, so there's the plot for Rayleigh equals 1000. Repeat the previous steps for the parameters 1E4, 1E5, and 1E6 to reproduce the remaining plots. So here's 1E5 plot, there it is, and 1E4 is 10,000, looks like that. So those gray lines are representing the X component of velocity. So as we're changing this Rayleigh parameter value, we can see how the X component of the velocity of the fluid changes. So if this is the X direction, and we already said the velocity in the Y direction is very high along the left and right boundaries, since it's the high temperature and low temperature, we can see the effect in the other coordinate, the X coordinate, by changing from very high values to, compared with the low value, it's sort of a, you've got two EDs, I guess you would call this. So you've got sort of contours on the top half and bottom half at lower Rayleigh values, given the same temperature delta, right? Because if we go back to the definition of the Rayleigh number, in the numerator we have Cp, the heat capacity, Cp times density of the fluid squared, times gravity acceleration, times alpha P, times temperature, times the characteristic length cubed, over the kinematic viscosity times K, which is the thermal conductivity. Alpha P equals the coefficient of volumetric thermal expansion, and Cp is going to be a constant, or we're treating it as a constant. For dynamic viscosity and density, we've defined both of those as constant. Coefficient of thermal expansion, alpha P equals the coefficient of volumetric thermal expansion, is given by this gamma term. So under heat transfer in fluids, fluid 1, where we define the velocity field, thermal conductivity, fluid type, density, heat capacity at constant pressure. This parameter, ratio of specific heats, there's only one material in here. So the ratio of specific heats must be 1 because they have the same alpha P, the coefficient of volumetric thermal expansion. So the other thing that changes, other than the gray contour plot, is the magnitude of the arrows. So the overall velocity of the flow inside the unit square decreases. So these arrows get lighter and lighter till they altogether disappear at low perimeter values of the Rayleigh number. All right, so that was it for today, and join me next time where I'm going to be doing, let's see, what's our next one? You can see which tutorial I'm going to do next by just going to COMSOL's application gallery and filter by discipline for COMSOL multiphysics, and I'm kind of just going in order here. So the next one is going to be beam with a traveling load. So I hope you enjoyed today's tutorial, and if you did, please hit the subscribe button and also like, comment, and share the video with a friend, and I'll see you next time.